Hello everyone, this is our C461 design project. My name is Andrew White. My group members are Aaron Prendergast, Ryan Abernathy, and William Sherwood. As we can see here, this is an overall layout of our job site. The activity we modeled on this site was of a moving of a gravel stockpile from one area of the site into another area, dumping the gravel that was moved, then returning to repeat this process. The gravel stockpile was located here where a Deere 544H wheel loader loaded a Mack CH613 dump truck. After the dump truck was loaded, it moved around the site, followed by the wheel loader, into a steep decline into the excavated basement. The big constraint on this activity was the two haul narrows located here that were unforeseen by the contractors due to constraints put on them by the university. In the site plans, the contractors were originally given an area over here to pile the dirt, but that was taken away from them for a parking lot, so they had to pile it over in this area, which gave them this haul narrow. After the dump truck gets to the bottom of the basement, it comes and dumps the gravel in the gravel dump. After the gravel is dumped, the dump truck turns around and returns to the steep incline. Here it is hooked to the wheel loader, waiting for it by a cable. After the cable is hooked, the wheel loader pulls the dump truck out of the steep incline. After it's pulled out, it waits for the cable to be unhooked, and the two return to the gravel stockpile and repeat the process. Data collected for this activity was collected through a window out of HM Comer. We found that we could see everything and record all the times needed from this location.
The on-site data that was collected can be seen below. On the left, we have the activities and the resources associated with them. The resources that were used for the activities were a truck, a loader, soil, space, a person, and cable. And they are on the right side of each adjacent activity. On the right, we have the collected data times for each activity. For EasyStrobe, we ended up using the average duration and standard deviation duration for all activities. So that's what they were inputted. The min and max, though, can be seen on the right of the graph, or of the chart. This is the model that we used for EasyStrobe. After the data was collected, it was input into the EasyStrobe system, and it was ran using the times and the constraints for each activity. The activity started with load, continued all the way around, and came back to load and repeated itself until the gravel stockpile of 1,667 cubic yards was empty, and the gravel pit read 1,667 cubic yards. This is our model validation. In it, we have the actual collected times and the simulated collected times. And since all the average and standard deviations for the actual and the simulated times all mirror each other pretty closely within a 2-second interval, we decided that they were of acceptable times. The overall time in days, seen in bottom in green, of the actual model was 2.823, and it falls between, that was the simulated model, falls between the actual model of 2.42 and the max of the actual model of 3.01. This, along with the fact that the 1.667 cubic yards was completely transferred as it was in the actual model, validate the EasyStrobe simulation.
In order to optimize our project's process, we first had to model the process in EasyStrobe. Once this was completed, we began playing around with the numbers and types of equipment. We ran the model many times with a variety of these combinations. The three primary changes we looked at were adding trucks, adding loaders and trucks, and changing the types of trucks and the effects that these changes had. It's clear to see that any addition of the original types of trucks has essentially a negligible effect on the project process. However, changes are noticed when loaders are added. The most significant changes are present when you add a loader and a truck, and you have two loaders and two trucks running at the same time. And finally, we want to see what changes would happen if we swap the current truck, which has a 15 cubic yard capacity, to a larger one with a 21 cubic yard capacity. As you can see, adding one affects it somewhat, but the greatest change observed occurs when you have two 21 cubic yard trucks running with one loader. If price or no object, swapping out the original truck for the two larger ones, then the current process will be optimized, yielding the lowest project duration and highest production rate.
So in order to determine which simulated alternatives are feasible, we performed a cost analysis. The cost data for each piece of equipment used was obtained from the 2010 RS Means manual. The total cost per hour can be seen in the far right column. They include equipment, operator, and overhead and profit costs. And according to RS Means, choosing a larger capacity dump truck only resulted in a $2 increase per hour. In the lower table, variances for each simulated alternative were calculated in comparison to the original or baseline model. For the simulation itself, it was determined that based on the very tight space constraint imposed unexpectedly by the university, that no more than 3 dump trucks could be present in this process. We couldn't add more than 3 dump trucks to the process. In order to optimize production and cut costs accordingly, we ran a simulation with larger dump trucks in place of the original 15 cubic yard truck, and making this small change increased productivity and drove down the cost significantly. As you can see, the lowest total cost observed from the simulation varies from the baseline by 28.6%, and this is using one 21 cubic yard truck. In contrast, productivity is maximized with 3 21 cubic yard trucks at a duration variance of 54.44%, and that would roughly cut down the production by 15 days of work. So in choosing the best selected alternative, we chose the equipment combination with both the highest production and the lowest overall cost. The best selected alternative based on the feasibility costs and production analysis would be to substitute the smaller initial dump truck with 2 21 cubic yard trucks. This cuts the total job cost down by almost 26% and lowers the duration of the work by 54%. Based on our model, making this small change in equipment type and number increased the productivity at a greater rate than the increased per hour cost, making it the most efficient alternative. In this project, it was really important that we kept the site conditions consistent when running out simulations, because increasing the confined space for the process would have changed the process we were trying to optimize in the first place. And for Doster, this was also unforeseen, but as stated previously, production can still be improved given the constrained situation.